But in practice, how do we get it? How do we actually analyze how stable this is? Yes? Yes. So remember how to analyze this is actually to use the relationship between E and tau as two vectors. Right? So here I'm just writing one equation, but actually I have as many equations as grid points. And I have as many unknowns as the grid points. So this equation, you can write it into matrix form. You can write a matrix X that is equal to kind of the block structure, the matrix we discussed over the last lecture. So basically you have a diagonal block that is tridiagonal, and you have off-diagonal blocks that are single diagonals, right? So you have this matrix, and I can write A times E equal to tau. So E is now the vector of the errors, and tau is a vector of the same length consisting of the truncation errors. And my A is a matrix, is a square matrix, right, as big as the number of unknowns and the number of equations. So what's the maximum or supremum of the possible E over possible tau? So the supremum, well, I can also write supremum of E over tau is actually equal to the supremum of A inverse of tau, right, divided by the norm of tau. Make sense? And this is actually, by definition, it's called the matrix norm of A inverse. Okay, so here let me say a few things. So for how many people it's the first time you see a norm of a matrix? Very few. Okay, so then I can go very quickly over this. So the matrix of the norm of a vector, I'm sure like all of you have seen before, right? You can say the one norm of a vector is what? What is the one norm of a vector? It's just the summation of the absolute value of Eij over I and j, right? So that's the one norm. Well, I mean, if you want to write it, okay. So what's the two norm? The two norm may be actually the most common C norm. Yes, it's kind of the Euclidean distance, right? It's the you first take the summation of Eij absolute value squared, and then take the half power, right? So, or if you write a P norm, you just replace the 2 here by P, right? Eij to the pth power and 1 over P. And over here you can see very easily why the one norm is defined as the sum of the absolute values. Just take P equal to 1 and everything follows. All right. There is one small caveat here is especially in numerical PDEs, there is a alternative definition of the vector norm. That is, before you take the power of 1 over P, alternatively, you may think of taking a 1 over the number of grid points, like n(m) over here, right? So you may actually so over here instead of the sum, you take the average. I mean, the reason is if you do the division, then the norm is actually going to be less dependent of the number of grid points or discretization. When you refine, so when you refine the grid, right? Even say your error, let's say you have a very bad scheme and your error doesn't decrease as you refine the grid, it stays the same. But if you don't divide by the number of grid points and just look at the sum of the error, you actually see the error would increase as you increase the number of grid points, right? Or let's look at a slightly more complex case. Let's say your error actually decreases inverse proportional to the number of grid points. It's actually a working method, but if you sum up the error as opposed to take the average, you actually seems to like your error does not decrease, right? Stays the same. So basically the convention, if you want to actually analyze the numerical error and how fast your solution error decays as you refine the grid points, actually remember to take the average, not the sum. All right, so that's a little bit different from the regular mathematical definition. I mean, if you ask a mathematician, they're going to say, okay, these two norms are equivalent, dividing by the number of grid points. For a mathematician, doesn't change the norm because of the definition of two norms being equivalent. Means one definition is always bounded from below and above by a constant times the original one. But when you actually analyze the norm for different grid sizes, please take the average, not the sum. Okay, so this is the vector norm. And the matrix norm, by definition, is actually, this is actually the definition of a matrix norm. Because the norm of a matrix is actually associated with the norm of the vector. So if you have one vector norm, you have the corresponding matrix norm, right? There are as many matrix norms and sometimes a little bit more, because some matrix norms are actually not some completely different definitions. But like if you have one vector norm, you can derive a corresponding matrix norm by saying, okay, so that's the supremum of A times whatever x divided by the norm of x, where both denominator and the numerator has to be that vector norm. Okay. So there is actually a lot of theories and analysis you can do to matrix norms. And one particular type of matrix norm that has been analyzed to death is the 2 norm. If you define the vector norm as the 2 norm, which is actually very convenient, right? It's just the Euclidean distance in generalized to high dimensions. The corresponding matrix norm actually is the largest, the absolute value, well, the largest absolute value of the matrix. Right, so it's also called the spectral norm. So that's something like we can always use in this scenario. Okay, so it also means that if you want to look at how stable this equation is, you grab the matrix A, and instead of looking at the largest eigenvalue, you know, like the inverse of A has the reciprocal of the eigenvalues of A, right? So basically you look at now the smallest eigenvalue of A to figure out how stable your system is. Right, clear? Any questions?